Today I'm going to go over equilibrium of a rigid body and how we can actually draw the free body diagram by identifying all the forces and actually drawing it. So let us take a look at what we try to achieve today. Our objectives are to identify support reactions and draw a free body diagram. There are certain activities associated with that, including a reading quiz, applications, support reactions, free body diagrams, concept quiz. There's also a group problem solving and an attention quiz that will pretty much wrap our today's topic. So first, let me go over a reading quiz. Let's read this together. If a support prevents translation of a body, then the support exert a blank on the body. And the correct answer is, as we have discussed previously, be a force. So if a support prevents translation of a body, then the support exert a force on the body. Reading quiz number 2, internal forces are blank shown on the free body diagram of a whole body. The question states internal forces, so it's very important to be able to distinguish that. In order for us to identify the internal forces, we actually need to cut the body at different sections to be able to identify all the internal forces. So internal forces are never shown on the free body diagram of a whole body. So keep that in mind. We would never show any kind of internal forces on our FBD. So let's take a look at some of the applications. This also provides me provides us with the importance of why we need to know statics and what's the application. An example of a truck ramp is given here. It has a weight of 400 pounds, and the ramp is pinned to the body of the truck and held in the position by the cable. So the assumption is, and this is pretty much pinned, and there will be no other types of movement except what is associated with a pin connection. How can we determine the cable tension and support reactions? We are going to use the principle of statics to solve such a problem. Also, how are the idealized model and the free body diagram used to do this? Again, if you look at two of these free body diagrams up here, this one and this one, we would like to know which one is more ideal. So we're looking at this guy here and this guy here, these two free body diagrams. Which one is idealized? Well, on the one on the left, this one, no external forces are shown. We can only see the kind of like a simplification of the ramp itself, and we don't have much information. We haven't identified much information on this particular, let's call this number 1, on figure 1, so we can be able to solve it. So let's take a look at figure number 2. As you can see, figure number 2 provides us with more information. We identify all the external forces that are associated with a hinge, and also the tension of the cable, and also the weight of the ramp itself is shown here, and A sub x and A sub y are the reactions of the hinge support at A. Other application, think of two smooth pipes, such as those that are shown in this picture, each having a mass of 300 kilogram. They're supported by the fork attachment of the tractor, and of course we need to be able to pretty much determine what all the reactive forces. Again, how can we make use of an idealized model and a free body diagram to answer this question? Again, this is a free body diagram. This is just a schematics of what's going on, but here on the free body diagram that I double check mark here, triple check mark here, the weight of the pipe is shown, the reactive forces are shown, also the reaction of the forklift itself at the connecting point down here. This is also shown. Again, the first thing we do is we try to identify all the forces. There would be a reaction here by the platform itself. There would be another reaction here. So in order for us to design such a system properly, we want to make sure that we can actually identify all the external forces and the connection of the condition of the connections, and also other things that we need to have to solve such a problem. So we have gone over some of these concepts here. I try to pretty much bring them all together and cover all the gray areas that we have not covered. Conditions for rigid body equilibrium. What are the conditions of a rigid body to be in equilibrium? Again, the body under consideration is shown here with blue, and I'll just put a red mark right next to it. In order for this rigid body, again, we have rigid body and we have non-rigid body, so we're going to make sure that we get our vocabulary correctly. Rigid bodies, they do not deform under the application of the forces. Now, that is really an oversimplification of the problem. Of course, if we apply a force to any rigid body, no matter how rigid it is, there would be some kind of a deformation. For this kind of problem, the deformation is assumed to be so small that it actually provide us with accurate calculations. So I want to make sure that you guys are aware of the real behavior of this kind of a rigid body, and then why we're using what we're using, and why it is so accurate for our purpose. So for a rigid body to be in equilibrium, the net forces acting on the body and the net the net moments must be said to be zero about a particular point. So, for example, summation of forces F1 plus F2 plus F3 plus F4 here is zero. If I also take the moment about any point on the body or outside the body, the summation of that moment about the point, either it's O or if it is O prime on the body itself, that should supposed to be zero. I butchered O prime really here, but that's what I meant, okay? And this is the point that I'm referring to. So that must also be the summation of the moments about that particular point must be zero. That's an arbitrary point. It could exist on the body itself or anywhere outside the rigid body. So how can we solve the problem that I've just shown you? The process of solving such a problem, rigid body equilibrium problem. First, we need to have some kind of an idealized model. This is called our idealized model. And then we need to have a free body diagram. Again, the free body diagram is a graphical representation of the body under consideration, in which all the external forces and moments would be identified. Those external forces include the weight or the gravity acting on the rigid body itself. It also includes the reaction of the supports, because they also exert forces on the body. Whether they are active or reactive forces, we would show all of them on free body diagram. Then we would need to apply the equations of equilibrium to solve for any unknowns. So let's take a look at the free body diagram here. The idealized model for a beam that is connected to a wall is shown here in this figure. There's also a force of 1200 Newton applied to this beam. That's the idealized model. The model on the right hand side, that is our free body diagram. And as you can see on the free body diagram, the weight of the beam itself is shown. Also, the 1200 Newton external force is shown. Also, what's shown here is the reaction of the support at point A. That's a rigid support. As such, there would be three reactions. There would be two A sub x and A sub y. Those are in terms of forces. And there will be one moment, M sub A. Note that there is always a possibility that some of those reactions would be zero. We have not gone that far yet. We want to make sure that we show all the reactive forces regardless of their magnitude. So whether they're zero or not, we would show them anyways, because I've seen too many times the certain components of the reactions would just left out because it turned out to be zero. But we want to make sure that we show all of them in advance. Then if any of those turn out to be zero, then we can set that to zero. But again, we want to make sure we show all of them on the free body diagram. Again, note that we show only the external forces and couple moments, and that includes the applied loads, support reactions, and the weight of the body itself. Okay. Then we would label them. As you can see, A sub x, A sub y, and M sub A. In this case, we call it M sub A because that's the moment at A. The labeling also plays an important role here. Excuse me. Proper labeling would help us to identify the reactions correctly, and it would really simplify the problem itself. So labeling is also important. Don't just label them any way you want. Make sure, for example, in this case, A sub x is the x component of the reaction at A sub y is the y component of the reaction at Y, and so on. Okay. So let's move on and take a look at the support reactions in 2D. There are different kinds of support that we are dealing with in statics. We identify them as a roller, we identify them as a pin or hinge, and we identify them as fixed support. So those are three main classification of the support reactions in two-dimensional. In three-dimensionals, we also have the same thing, except the reactions would be different. It would be in three-dimensional instead of two-dimensional. So it's important to realize why we call them the way we call them. The smooth pin or hinge, we call them smooth pin, assuming that the friction is zero. What we are dealing with when we talk about the support reactions is the modeling of the real behavior of this kind of support. The modeling is pretty accurate. Ideally, there is no roller or fixed support because roller support, they exhibit some kind of a non-rolling reactions. Fixed support, they also exhibit some kind of a reaction that is not going to be 100% fixed. So this is the real model of what we see out there in the real world. and it is pretty accurate for solving static problems. When we're dealing with more advanced topics, of course, we would consider all other aspects of a support, but that's beyond the scope of what we're dealing with in statics. So a few example sets of diagrams are shown here. Please note that for a roller, the reaction is perpendicular to the surface in which the support itself rolls on or rolls over. Both terms are used. In this case, there is an angle of theta since the support is put in place as you see the way it is. F would be perpendicular to the surface. It may not necessarily be perpendicular to the arm as shown here. There is only one support reaction in this case since the support is free to move in this direction, but it's not free to move in this other direction. Okay. For a pin support or a hinge, there will be two reactions, F sub x and F sub y, as shown here. This particular support is not free to move in the x or in the y direction. The movement, the displacement of the support in the x and y directions, they are prevented in such a support, but it is pretty much free to rotate around the point that is shown here. Okay, so it can rotate both this way, and it can also rotate the other way, right? So that's very important to realize. So as a result, there will be no reactive moment, and the moment would be 0. For the fixed support, we are going to have reactions in terms of forces and in terms of moment. In this case, they are shown as internal. However, if this is the end of the support, it's going to be shown the way you see it. So these are three main support conditions that we're dealing with. It's very important to understand them and know how to deal with them. They're also given in your textbook if you're interested to also study them there. So let's get more tuned in with the correct terminology. As a general rule, if a support prevents translation of a body in a given direction, then a force is developed on the body in the opposite direction. That would be called a reaction. Similarly, if rotation is prevented, of course, a couple moment would be exerted on the body in the opposite direction at the point in which it is prevented from rotating. So that's the absolute correct terminology that I just used. Let's take a look at an example. In this particular case, the operator applies a vertical force to the pedal so that a spring is stretched 1.5 inches and the force in the short link at B is 20 pounds. So this is A, this is B, this is the pedal, this is his foot. It's covered with wet concrete. That's why it's difficult to see. So he applied a force to the pedal, and we would like to see, we would like to draw an idealized model and a free body diagram of the foot pedal. So would you be able to identify all the forces that would be exerted at point A and B before I move on? Well, let's double check to see if you have done it correctly. The idealized model would be drawn as you can see here. The distance of 1.5 inch is also provided here because the spring is stretched by 1.5 inches, as you can see. Also, there are other information given here. The force F that would be exerted on the pedal by the foot of the operator is also shown here as F, capital F. The length of the pedal from the point the force is applied to point A is also shown as 5 inches, very important information. And the distances between point A and B is also shown here. Point A is down here. If you continue this, so the vertical distance would be 2.5 inches. 1 plus 1.5, that'd be 2.5. The stiffness of the spring is also shown here. So just looking at this model, they would be reactions here, and there would be reactions here, right? Would it or would it not? Let's check. Here we go. At point A and B, and there would be A sub x. Again, that's the x component of A because A is rolled at that point. As you can see, there will be no moment about point A. The 30-pound force that would be developed here would eventually translate into the reaction at that point. And also for point B, there would be a reaction which would translate into that 20 pounds force. So it's very important to realize at A there is a pin, and as a result we only have reactions in the x and y directions perpendicular to the point A. Now, are you ready for a concept quiz? Well, let's go over this concept quiz together, and hopefully that help us a lot with clarify what we have covered so far. So the beam and the cable with a frictionless pulley at D support an 80 kilogram load at C. In a free body diagram of only the beam, and there are how many unknowns? Remember, the free body diagram of only the beam. How many unknowns are here? We need to identify them. There's an 80 kilogram load at C, so this is known, right? This is known. There we go. So how many unknown is here? Again, we're just looking at the free body diagram of only the beam itself. How many unknowns are here? I want you to think about this. We are just looking at the beam, so we're not considering B and E. So here, how many we're going to have? There'd be 3 forces reacting here. One is here, one is here, and we assume that there is a frictionless pulley, and we don't have much information about this condition actually. So for now, let's assume that there are 3 forces on this free body diagram of only the beam. Let's take a look at the next one. If the direction for the setup that's shown here, if the direction of the force and the couple moments are both reversed, what will happen to the beam? So as you can see right now, the moment is applied at this point, that is a counterclockwise moment, and the force applied is also have a tendency to hold the system in place, in this case the beam that ends with a roller. So at the end of this, now we are going to have one reaction exerted at point A by the support. Okay, it's perpendicular to the surface in which the roller rolls over it. As you can see, if we reverse the situation, that means we're going to pretty much provide an opposite to what you see here. So that's kind of like this way actually, which is the same as what I've drawn. So, and then there would be a force, a couple moment acting the other way, right? Of course, in such a system, we have a tendency to pretty much turning the system to the right of the page, right? So it's kind of like we are turning it this way if we reverse the situation. So the beam would actually lift from A. It's not going to be lifting from point B because that is a pin support. It's the roller support that we have at A that can cause this to rotate clockwise. So the beam will lift at B if we if you reverse the direction of both the force and the couple moment for this particular system. Let's do a problem and solve this problem together, and then we would move on. For this particular setup, for this particular machine, we would like to draw a free body diagram of the crane boom, which is supported by a pin at A and cable BC. So we have a pin at A, the information is given, and the cable BC also shown here. The load of 1,250 pounds is suspended at point B, so that also given. So this load is known, and the boom weighs 650 pounds. That means the weight would be applied at the center of gravity of the boom. Now later on we are going to have lectures on how to calculate the center of gravity, but for now that would suffice since it's given. So we want to go from the boom to a free body diagram and draw that. We need to know the condition of the supports. At A it's given. There'll be two reactions at point A sub x, A sub y. There'll be no moment since that's a pin connection at point A. At other places, of course, we have the 1,250 pounds of the weight of that we try to support. If we continue this force down here, we would get the tension in cable BC, identified here as T sub BC. Also, the weight of the crane must be applied at the center of gravity. So we apply that 650 point at point G. That would be another force that is shown here, and that would give us our free body diagram. Let's take a look at another group problem together, and then we would actually look at an attention quiz, and we wrap our today's topics. So let's take a look at this system that's given here. We would like to draw a free body diagram of member ABC only, and we're not concerned with the rest of it. Member ABC is supported by a smooth collar at A and a roller at B and the link CD, right? So if you want to only draw the free body diagram of ABC, as shown here, we are going to have one reaction, one external force at the end of C. I assume an arbitrary direction as long as I stay consistent with my arbitrary assumption, then I should be okay. For example, I would can assume all the forces in one direction and whatnot. Later on, we are going to do more problems, and you would see a much better picture of our sign convention. So we can really have it both this way, or it can be the other way. Or also on this one, we can also do the same thing. And the link B, we would also show that. Remember that there's also a support here, so there will be a reaction, I assume, upward as positive in this direction. But again, if we assume one sign convention for all the forces, then we would go ahead and solve the problem. If the sign of each of these forces need to be reversed, then the result would be negative. Then I would go ahead and switch the direction of the forces around. So here again, we are going to have one force here. We're going to have a force at CD. We're going to have another one at support B. And that's how our free body diagram it would look like. The 4 kilonewton meter moment is actually an external moment. As such, that would be shown also down here. And the reaction of the supports and member CD would also shown the way you see it here. Note that the angle, of course, remains the same. We only show that on a free body diagram the way it is, and the distances are also shown here. It's very important to show the distances on a free body diagram because when you deal with more complicated systems, you're going to have different moments caused by different forces, and that would help a lot if we identify all those on a free body diagram. If we don't, then it's much easier to make mistakes. So take a look at an attention quiz. I mean, take a look at the first one first. Internal forces are not shown on a free body diagram because the internal forces are blank. And we need to choose the most appropriate answer in this case. Because they're equal to 0, no. And they may or may not be equal to 0 because they're negligibly small. No, that's not true. Because they're not important. That's not true either. They could be very important. Because the correct answer is B. They're equal and opposite, and they do not affect the calculations when we're dealing with free body diagrams. That's really the main reason. The second question, how many unknown support reactions are there in this particular problem? Is it 2 forces and 2 couples? Is it what is it? So let's identify that here. This is a roller, so we're going to have one reactive force here. This is rigid, so we're going to have one force in the x direction, one force in the y direction, and there would definitely be a moment. Let's assume the direction of the moment to be counterclockwise. So we're going to have 3 forces and 1 couple moment. So the correct answer is D, 3 forces and 1 couple moment. That brings me to the end of today's topic. Let learning continue. If you have any questions, please feel free to contact me. Thank you.